Okay. All right, so the first thing is there's test 4, exam 4, Friday the 21st. And the topics are going to be everything up through stresses and beams. We still have one topic to get through for stresses and beams, but today I want to work on a problem where we're just going to put everything together up to what we have now. Anyone have any questions about the exam? Yeah.
Tension stress, like vary over the cross section YZ. Why it's only very along X, not the YZ line. And when we do the tension, stress tension,
yeah,
it's using the YZ
line. So
yes.
About Q.
Yeah.
Is Q along the neutral axis always going to be 0? Basically.
Yes.
Okay.
No. Sorry. No, the stress along the neutral axis, the stress due to bending moment is equal to 0. But along the neutral axis, Q is the biggest it can be because you have the biggest area you can have. And so yeah, Q is at a maximum at the neutral axis. And because of that, the stress, the shear stress, is due to the shear stress due to shear force is maximum along the neutral axis. And that's why with a circular cross-sectional area, we can only calculate the stress due to shear force for a circular cross-section at the neutral axis. The only reason that's such a little bit of information to have about it, but the reason that's useful is because that happens to correspond to the maximum shear stress. Yeah, so for a circular cross-section, we're talking about this area. The centroid is here, and we're talking about this being that distance D. Y. Oh, right. This is that line Y1 or whatever I called it. That's the only. So remember, with a rectangle, you pick that because we can do this calculation for any location. But for a circular cross section, we can only do it for this. Yeah, I mean, in this case, our Y1 is the neutral axis. It is the Z axis. That's the only place we can do this calculation. Okay, so this D, who remembers the formula for the centroid of a circle? We could derive it. Let's not. I think it's 4 pi over 3r, maybe? Something like that. It's the same as for a quarter circle. That's just the location of the centroid,
Oh, yeah.
is what I'm looking for. Or a quarter circle, it's the same. I think
4R over 3 pi.
no, 4r over 3 pi. Okay, so 4r over 3 pi. That's just the distance from the neutral axis to the centroid. Okay? And so in that Q formula, that's D. And so Q is equal to the area times D. No, the area above that line. And so it's half of the area of a circle. So that's pi r squared over 2 times the distance, 4r over 3 pi. The pi's cancel. And so you get 2r cubed over 3. Yep. And then since that's the only place that you can calculate the stress due to shear force, let's see. This is the shear force, negative shear force times Q over IB. I is equal to, we have a formula for that, pi r to the 4th over 4. Pi r to the 4th over 4. And B is the diameter, so that's just 2r. And so for a circular cross-section, you can only calculate the stress due to shear force along the neutral axis, but you have a single formula that works for everything. So this is equal to negative V times 2r cubed, let's see, 2r cubed over 3. So that's V times Q over I. E. What? Those are like parentheses. That's how you do it in chemistry, right? Jeez. That seemed unnecessarily sensitive about it. Yeah, it's just, yeah, right. Okay, so now we can cancel some of this stuff. We have 5 R's there, 3 there. We have, so negative. Oh yeah, 4/3. 4/3, pi on the bottom, and then r squared, something like that, right? Times v. So if you're trying to calculate the stress due to shear force with a circular cross section, you can only do it along the neutral axis, and it's always this. Yeah.
Well, why is that? Assume I don't really get it because we know the distance we go, but the area will be smaller. Just depends on the area and the distance. So I would have like large, like very large.
Okay. Let's I think this will be worth doing. Hopefully this won't take too long, but let's compare. So 3 beams containing the same amount of material loaded the same way. Which will deform more due to, a couple, due to bending? Okay, so here are the 3 candidates. Let's say one is 1 meter tall and 1 centimeter thick. One is, you can think of it being the same beam but just bending the other way. So 1 meter wide and 1 centimeter tall. And then the third one, let's say, is a circular shape where we have to have this R. We can calculate it. Pi R squared, the area of this has to be equal to the area of these two. So that's pi R squared has to be equal to 0.01 meter squared. And so R is equal to 0.01 over pi square root. Can someone tell me what that radius is? These are cross sections. So we're talking about this being the bending axis. That's the Z axis. You're looking down the front of the beam. The beam goes from you into the board. And you're trying to imagine if you hung on the end of this long beam, how much it would bend down.
Yeah. So you're looking straight like that.
Yeah.
Okay.
So what's that radius?
I have the radius, but would that cross section be that value? Because wouldn't it be the cross section of the side that 0.1 is on?
The length of the beam, the x-axis is going into the board.
Okay.
This is the YZ plane. We're just looking at the cross section.
Okay. Yeah. And it's 0.0564 meters.
Okay, 0.0564 meters. Okay, so what's your guess on the deformation? Which one of these, if you're trying to build something that under this certain load is going to, and you say you hang on the end, and you need your weight to pull it down less than a centimeter, say, which one of these is going to be the best and which one is going to be the worst? B is going to deform the most. And then what's going to be second? C is going to be second, and A is going to have the least deformation. And so what we're going to do is we're going to calculate the area moment of inertia of these 3. This is going to be the highest, second highest, lowest. And then the idea is, if you look at the formula for the stress, the formula for the stress is inversely related to that value. So you're going to have the smallest stress with this one, the next smallest stress with this one, and the biggest stress with this one. And because stress and strain are proportional, they have that linear relationship. That means that this has the biggest strain, the biggest deformation. This has the next biggest deformation, and this has the lowest deformation. Yep.
So we're applying like that law.
Yes.
But it's not going like this. We're applying not like applying like that.
So here's what we're talking about. I'll just draw one of these beams, but so this is the cross section. Okay, so this so this is 0.01. This is just A, yeah. This is 1 meter, and then this is something that's not given in that cross section. We're saying if you apply a force here on all 3 of these beams, which one is going to bend down the least? Yes, or a round thing. Yep, exactly. Diving board or a balance beam. Diving board or a razor blade.
And the question is, what's going to bend more?
Yeah, which is right. So the one that's going to bend the least is the one with the biggest area moment of inertia. And the reason for that is because the strain, remember, is proportional to the stress, and the stress is equal to my over I. And so if you have a big value of I, you're going to have a big absolute value of deformation. If you Well, this force is going to apply no matter what beam you have. This force is going to cause the same internal loads the whole way along the beam. Because remember, calculating internal loads, you don't care about the cross section. It doesn't come up until you start calculating the stress. So we have the same internal loads in all 3 of these cases. The same M everywhere. The question is just which one of these cross sections is deformed more by that bending moment. That's just the cross section for part A. Yeah. Yeah, well, it would have the same dimension long wise, just the shape of the cross section would be different. So this is the x-axis, y-axis, z-axis, and then here we're talking about z this way. Okay, so
Will you please
no, I can talk to you about that after if you can't figure out what's going on there. But all of these are just the YZ plane, and so one more time. Which one of these 3 is going to have the bigger area moment of inertia? The biggest one. Yeah, A is going to have the biggest, and that's going to mean the smallest deformation. And then second biggest is C, and then the smallest is B. Okay. Yeah. What?
I said my eye. Well, just that my over I.
Oh, yeah. Oh, yeah. My eye, right. Yeah, remember my eye. Negative my eye. Okay, so for part A, the formula for that, I is equal to the base. Did I say base or width? I think I said W. It's WH cubed over 12. So that's 0.01 times 1 cubed over 12. So that is 0.00 1/12. What is it? No, it's the other way. 1 over 1200. 1 over, yeah. 0, 0, like that. What are the units? You're thinking of the other kind. Meters to the fourth. No. Yeah. Something. Yeah, right. That's for the one that's taller than it is, the rectangle that's taller than it is wide. The second one, the diving board, this is your hang. So just close your eyes and imagine yourself hanging from the end of a razor blade with all your weight pressing your fingers down against the razor blade. That's the first one. Yeah, that's true. And then,
No, I'm not getting
Yeah, maybe.
like I'm the only one.
okay, so this is C, is the circular cross section with that same force applied. Thanks. You still have that same force F acting down. So you have the same beam, but you're just changing cross-sectional shape in A, B, and C. So for this, well, that was C. So now we're doing the calculation for B. That's a rectangle again, so we have this. But now we've switched which one is the width and which one is the height. So the width is 1. Height is 0.01, and that's the one that we cube, divided by 12. And so that is 8.3 repeating times 10 to the minus 8. Okay, so that's much, much smaller area moment of inertia than A. So which one of those is going to deform more? Right. The one with the lower area moment of inertia deforms more. And the reason is that I appears in the denominator. And then the last one is the circle. I is equal to pi r to the fourth over 4. So that's pi times 0.0564 to the fourth over 4. Can someone calculate that? And so you get exactly the relationships between those that you sort of intuitively have. I have a bicycle. So for steel, that's not the end of what I was saying. Okay, so most steel bicycles have my bike frame. Usual modern steel frame is like this. So we're looking at a cross section of the tubes. Okay, a bike frame isn't solid steel. Well, a lot aren't steel at all, but a steel bike frame, it's not solid. That would be incredibly, shockingly heavy. They're tubes. And a modern one has a thickness of about 1 millimeter. So 1 times 10 to the minus third meters. And I don't know what the diameter is, but let's say the diameter, the radius, the outer radius is 2 centimeters. How much is 4 centimeters? Let's say 2. I think that seems pretty reasonable. Yeah. Yeah. So let's say it's like that. Okay. But I have this bike that I really like, even though it was cheap in 1973. My cheap 1973 frame has tubes like this. Let's say they're let's say it has a radius of, let's just say 1 centimeter. And a tube thickness of 3 millimeters. Three. Okay. So just think roughly about what the differences are here. So first of all, we can calculate, well, first let's calculate the area. So the mass of this thing is proportional to the volume. So if we assume all the lengths are the same, then the difference in mass is just going to relate to the difference in cross-sectional area. So the area here is pi 0.02 squared minus 0.019 squared. Did I do that right? Can someone calculate what that area is? It's 1 millimeter thick. So So the outer radius is 0.02, the inner radius is 0.02 minus 1 millimeter. 1.225 times 10 to the minus 4 meters squared. And then this one is pi times 0.01 squared minus 0.009 squared. So what's that?
.007.
2.007 times 10 to the minus 4? Oh, yeah. Thank you. Yeah, okay. Okay, 1.6 times 10 to the minus 4 meters squared. Okay, so my old bike is heavier, you know. It has a bigger area, so it has a bigger volume, so it has a bigger mass. That's not a desirable trait in a bike. Yeah. But a lot of times you add material to a bike to make it stiffer. Like if you're trying to like race a bike, you want a racing bike, you want it to, when you pedal down, you don't want it to bend. So adding material can give you the desirable property of having a frame that stays stiff when you apply bending moments to it. But so now let's calculate the difference in the area moment of inertia of these two. Okay, so for this one, well, let's first just think about what, the formula for a hollow tube. We can do this with the summation formula. I is equal to pi r outer to the fourth over 4 minus, so that's the area moment of inertia of the outer circle, and then subtract the area moment of inertia of the inner circle, so minus pi r inner to the fourth over 4. And so for this one, I is equal to pi times 0.02 to the fourth. Let me do it like this. Minus 0.019 to the fourth. And for this one, you have pi over 4 times 0.01 to the fourth minus 0.007 to the fourth. You see what I'm doing on that? And so what do you get for this one? This is like a modern... Yep, meters to the fourth. And now for this one, 5 point, so let me write that as, that's 0.597 times 10 to the minus 8 meters to the fourth. And so if what you want to have in the tubes that make up a bike frame are tubes that are as light as possible and as stiff as possible, then this cheap old frame sucks in every way, And that's why they build it like this now. You have a lighter frame that still manages to resist bending deformations better than this old way. So yes, so exactly this. So the new one develops less stress, And because it develops less stress when you multiply it by the compliance matrix for steel, therefore you get a smaller strain. And so it bends less. And so even though this old bike is heavier, when I go down, like hit bumps or like pedal hard or whatever, I can feel it like, wow. I mean, it's not like you really notice it when it's flexy, it's bendy, it feels bouncy, which is actually sort of fun, But for like a bike racer, that has all the traits that you would not want. And so a calculation like this sort of lets you figure out how you want to design things,
Make it like this instead of that also.
Yeah, we don't have a way to calculate that stuff. You'd have to build it up, like approximate it from simpler shapes. Yeah, or do the integral. You could use the integral definition. Yeah. So it has to do with the outer radius versus the wall thickness, and changing those things changes all the properties. Right. It bends more easily. Yep. That's right. You're thirsty? Oh, yeah, it's interesting. It is interesting. Yeah, it's that. So it comes from this formula here that the stress is inversely proportional to I. So if I goes up, the stress is smaller. If I goes down, the stress is bigger. And so really, like, if those are the only two parameters you're using to design this thing, it would make you want to design a tube that's this big and so thin, like paper thin. But there's other stuff that comes into it, because then if you bump that with a pedal, it would crumble. But this difference does explain why the cheap old one is heavy, and still, even though there's more material there, it also feels bouncy. Yeah. Well, it just depends what you're trying to accomplish. I think in most engineering applications, yeah, you would prefer higher area moment of inertia because you don't want deformations usually. That's not always true, but more often. But you always want as little material as possible because it's cheaper to make stuff with less material. Okay. Yeah, well, that's good. Yes. Yeah. XY, that's right. This is always XY. Yeah, then we're going to have to do more figuring. So the restrictions on the beam types. So yeah, I think that's really useful to go through. Let's just go through all of them so far. So restrictions I don't want that. Restrictions for beam stresses. tension, there's none. Bending moment, that's right. Yep.
Why do you get the pigmented shapes like
Okay.
yeah, same like
Yeah. So
yeah,
yeah. So the prismatic ordinary again. So that just means that uh, even if it's square all the way down, you could have it be a small square at one end and a big square at the other. Yeah. So it has to be a shape that you can make in the Play-Doh Fun Factory. You know what that is? Yeah. Or it has to be a shape that you could make with a toothpaste tube. Yeah, you could extrude. Um, and there's one more. I don't think I'm doing them in the order I gave them to you. There's one more. There's one more. That's right, symmetric. And it has to have the right kind of symmetry. So this is okay because it's symmetric about that.
That's just a cross section. You're looking at it.
Right. So it has to be symmetric. The cross section has to be symmetric about the y-axis, or the y-axis has to be a line of symmetry of the cross section.
so basically for epoxy
Yeah. Yep.
you have to be all three.
Yeah, it has to be a mirror image across the y-axis. And then the last one is shear force. And what are those restrictions? Yep, rectangular cross section. Just in time for class. Yeah, so cute. Oh, all right. That's all right then. Rectangular cross section. Okay, so rectangular cross section or circular cross section along the neutral axis only. Oh yeah. So rectangular cross section, and it has to be tall, not fat. So if you wanted to calculate the stresses in a beam like this, this is a cross section. Imagine extruding that out to make a beam. Well, you could calculate the stresses due to tension in this beam. You could calculate the stresses due to bending moment in this beam. But then when you got to the step where you're trying to calculate the stress due to shear force, to combine all these things into then at that point, you're stuck. You couldn't do stresses due to shear force for that shape. If you were trying to calculate the stress on a beam like this, and for some reason you happen to have no shear force at the point you're looking at, then you could do it, you know.
Could you say like the two lobes are kind of like circles and then the bottom part's kind of like a rectangle?
No, not really, because, yeah, not really. What? Because it works for bending, but it doesn't work for shear force. So you have to think about, so if all you want to calculate is the stress due to tension or compression, it doesn't matter what the cross-sectional shape is, you can do it. If you're trying to do it just for bending moment, then you only have to meet these requirements. If you're only trying to do it for shear force, you have to meet those requirements. Yep.
Two-part question. The shear force, is that what you went over on Friday?
Yes.
Okay, part two. Are those notes, will you be posting those notes?
Yes, I'll do it right now after class.
Okay, thank you.
Yeah. Okay, I'll do that too. I'll do that right after class. What? For cork, yeah, we haven't done it yet, so I'll talk about. It has to be round, I think. It has to be round or thin-walled. Okay, that's all.